I believe the current mandate from Congress is that we need to discover more than 90% of all these near-Earth objects that have diameters greater than 140 meters. And Pan-STARRS is really the leader in discovering these things. In addition, it's also leading at discovering not hazardous things, but things like Oumuamua or very faint fuzzy comets in the outermost solar system. So it's really providing a rich array of science for planetary folks.
Aloha, everybody. Welcome. I'm Michael Bruno, Provost at the University of Hawai at Mānoa, and I'd like to welcome all of you to our 8th webinar in the UH Community Conversations series. Our topic today could not be more fascinating and fundamental: the evidence of visitation from outside of our solar system. Our guest to lead us in this conversation is one of the university's most esteemed scientists, Dr. Karen Meech. Karen is an award-winning astronomer and astrobiologist, and she is presently also serving as the interim director of our Institute for Astronomy. She's been on our faculty for more than 30 years and has served as co-investigator on 3 different NASA missions. Most importantly for us today, she led the UH team that made one of the most exciting discoveries in astronomy in recent years: the confirmation of an object passing near Earth that originated far beyond our solar system, an object that her team named Oumuamua. Her TED Talk on that subject has more than 8 million views, and I'm going to come back to that talk later in our conversation. Thank you so much for joining us today, Karen.
It's a pleasure.
So a word on the structure of our program today. We're going to talk for about an hour about Oumuamua, on the search for extraterrestrial life, and on the university's outsized role in the detection and tracking of near-Earth objects. So, Karen, the object we're discussing today was first detected in 2017. Maybe you can walk us through a bit of the story. I remember when we spoke way back then, you kind of hinted at learning about the true value of adrenaline in those days that followed the initial discovery. So why don't you tell that story, a little bit of that story to the audience?
We have the Pan-STARRS telescopes that are funded by NASA to survey the night sky to look for potentially hazardous objects, things that come near the Earth. And it just happened, I'd been working really hard. I'd just come back from a scientific meeting. I hadn't had a day off for a couple of months. And so finally I had Sunday off, and Richard Wainscoat, who was the PI on the NASA-funded program, called me at home and said, "I think we found an interstellar object." And my first thought, I didn't tell this to Richard, was, did it have to be today? This was my first day off. But in fact, I got really excited. And what had happened was Rob Werk, who is working with Pan-STARRS, had seen it in the data stream on the morning of the 19th of October. And it looked like a rapidly moving object. And like many of the near-Earth objects, they look backwards in the data to see if they can find data on previous nights and get a preliminary orbit. And they did find it on the 18th, but 2 nights isn't enough to really say much. That gives you a straight line. But by the 22nd, with more data from Mauna Kea using the Canada-France-Hawaii telescope, they were convinced it had a hyperbolic orbit, meaning it wasn't from our solar system. So that's when Richard called me. And that's when the adrenaline spiked up, because I realized my day off was over and we were going to have to scramble and secure telescope time on telescopes all around the world. If we could have the first slide, this just shows what the Pan-STARRS telescope looks like on Maui. And the facility scans the sky every night when it's clear, obviously. and looks for moving objects. There's now 2 of these telescopes. So that led to a huge campaign to characterize it, but we only had about a week to do it before it got really too faint for the main science.
And it struck you and your colleagues because it behaved in a different way from what one would expect with an object like this, right? Can you explain that?
Well, the orbit was what really caught our attention at first. But the second thing is we started to observe it. We'd long predicted that these sort of objects would be entering our solar system, but the predictions expected that the very first one would be a comet. Typical comets are small bodies left over from the formation of the solar system made of ice and dust. And when they get close to the sun, the ice warms up, pushes the dust off, and gives us a tail. And that makes it easier to see. It gets brighter. So we thought the first one would be a comet, and this didn't look like a comet. The orbit had brought it really close to the sun, inside the orbit of Mercury, and it was outbound. It was on its way out. It had already passed the Earth when it was discovered. So it was surprising it didn't have a comet tail. We also looked at its brightness as a function of time, and the variation was huge. Again, a little bit atypical of solar system bodies. And then the most unusual thing that I'm sure we're going to talk about later is that it wasn't just behaving controlled by the gravity of the planets. It was actually accelerating away from the sun.
I remember early on you said that acceleration was really unexplainable, or at the time perhaps unexplainable. I know we are going to come back to that. Let's talk a little bit about the name and how that name came about and its significance.
Yeah, this was the first of its kind, and you really want to think carefully about the first of its kind whenever you discover something. And we thought, in honor of it being discovered in Hawaii by astronomers at the University of Hawai, we should have a Hawaiian name. So Doug Simons actually suggested that we contact some native Hawaiian experts in linguistics at the Imaloa Center and gave them 2 days to suggest a name to us. And so they came up with the name Scout or Oumuamua, which means scout or messenger sent from our distant past to reach out to us.
Wonderful, wonderful. Thank you. So Karen, we've had a lot of questions come in from the audience, many of them as the audience members registered. One asks, since its discovery in 2017, Oumuamua has been classified as an asteroid, a comet, and even a space probe. Why is it so difficult to categorize it?
Well, partly because we don't have a lot of data. Most people don't realize we had only good data for a little over a week, and then it got too faint. There's a little bit more data all the way into January, but we didn't have much time to get much information, but we did a phenomenal amount in that short period. Now, comets, as I mentioned, they develop tails as they're outgassing. Asteroids don't. That used to be the traditional definition, but nowadays we've seen comets that go dead. They stop outgassing. We've seen asteroids with ice on them. So the definition between the two is a little bit blurry. But Oumuamua definitely had no dust seen around it. But on the other hand, the only rational explanation for its acceleration was that it had gas coming off. And therein lies the controversy. You can't really prove it because we didn't have enough data to say definitively that it's outgassing.
Yeah, yes. I remember, and I know that's continuing. And we'll come back to some of that discussion a bit later. So you led the team that analyzed the object's brightness, the fluctuation in the light, and reflectivity. Can you describe how you did that and what you and your team found?
Yeah. In fact, if we could bring up the slide number 5, what this is showing is a series of pictures of Oumuamua that was taken with the Canada-France-Hawaii telescope. And you can see Oumuamua in the center in the yellow circle, and it's really faint. And so what we did, these were data from Richard Wainscoat. He took a whole series of pictures, and so you see it's kind of jerky because we're looking at one after another. The streaks are the stars it's passing between. And you can see as we're talking, it's getting brighter and brighter. Now, if you go a step forward on the sequence, we will see what we call the light curve. And this is a plot of the measurement of the brightness as a function of time. So you can see it's going up and down as it gets brighter and fainter. And what that's doing, so thanks, is we're looking at an object that's an irregular shape. And once the slide comes down, we can take a look at my mouse. And most comets aren't spherical. And so you'll have an irregular shape. And what we're seeing is the reflected sunlight coming off of the side of the object. And then as it rotates, you have the small side. And so we get less light reflected. And so that's what we're looking at. And so that's how we characterized the rotation. So that tells us how frequently it rotates, roughly about 3 times a day. Also, the relative brightness tells you how big it is if you know how reflective a surface it has. So that's how we characterize the reflectivity and its size and effectively its shape.
So what do we know? Let's talk about the shape. What do we know about the shape of the object?
Well, if this were a perfect sine wave, we would have a good idea about the shape. But as you saw from the light curve, it didn't look like it matched up perfectly. So in fact, on slide 6, we have the first interpretation of the shape. And this is by virtue of the fact that there was a brightness difference with a ratio of 10 to 1. That suggests to us the ratio of the axes is 10 to 1. But as you notice in this picture, the whole surface isn't illuminated because we're looking at it in an angle. So you can see the bright sunlit portion and the dark shadowed portion on the back. So this one actually looks longer and narrower than it really is. So from that reason, we estimated anywhere from 10 to 1 axis ratio all the way down to maybe 5 or 6 to 1 axis ratio. But that's unusual because we've never seen anything like that in the solar system. On the other hand, what we discovered was this thing isn't rotating simply, it's wobbling like a top. So while it's rotating around one rotation axis, it's also nodding up and down and rolling back and forth. So if we have a simple rotation, it's also oscillating this way and nodding up and down. And that makes it much more hard to interpret the shape. So slide 7 shows an alternate interpretation. This is a beautiful painting done by Bill Hartman. He's a space artist. And this is his interpretation of what it might like. He tried to make it red. He's put some impact craters. So all the details are his imagination, but it could be more of a flattened pancake.
What would cause the formation of an object with this kind of a shape? You said there hadn't been something seen like this in our solar system.
Well, the hardest one to explain is the long cigar-like shape. The flattened shape is a little bit easier to explain. And I don't have any images for this, but if anyone wants to Google Saturn's moon Pan, P-A-N, it has the most bizarre shape. When I first saw it, I thought this has to be a fake image. It looks like a UFO. I mean, it's got a ball with a ring around it. And there are some theories now of how this formed due to collisions in Saturn's rings. The New Horizons spacecraft target, Arrokoth, the Kuiper Belt object that was flown by, looked as if it were 2 things that had collided together. And one of them looks very flattened, like that Oumuamua picture. I don't know that they completely explain the shape on that one, but we've seen them natural in our solar system. The really elongated cigar shape is much harder to understand because, we think these are building blocks of the early solar system that have been kicked out. And anytime you have these violent processes, there's collisions, and that would break them apart. So even if you started with something really long, it should fragment and get shorter. So that has led to much speculation on all sorts of ideas on how to form something like this.
And it sure does look like a spaceship, I have to admit. So, and I know we're going to get there, but I remember that early on in that first year, you were very focused on what exactly might the composition of Oumuamua be. Can you talk a little bit about that?
Yeah, the way we go after composition is through spectroscopy. In other words, we're trying to measure the amount of reflected light at different colors. and different chemicals will absorb different wavelengths of light. And so that can give you a fingerprint or map of what's on the surface. Unfortunately, we couldn't get a proper spectrum in great detail on Oumuamua because it was too faint. We didn't have much time, but we were able to measure different colors on the surface. And it was red. And that means it reflects more red light than it does blue light. It doesn't mean that it's going to be a bright red color. And in fact, in slide 9, we have some examples of what red means for solar system objects. And in the bottom images on the lower left, this is just a black and white image of the Rosetta spacecraft target 67P Churyumov-Gerasimenko. This is black and white. But the picture next to it shows the picture in true color. And that is a red comet surface. So that reflects more red light than blue. And the reason for this is that it's organic rich. On the other hand, the thing right next to it, the two panels to the right of it in the bottom, this is Saturn's moon Iapetus, and the front side is red. The back side is white looking and it's icy. And the reason for the strange dichotomy on this one is because it's moving around the orbit and it's collecting dusty debris on the surface. And this one is not red because of organic compounds. It's red because it's got a lot of iron minerals on the surface. Now, the top two figures on the left shows an actual color image of Oumuamua that looks slightly reddish. And then the one on the right is just black and white from HST. The point is, it's red. That makes it look like a comet, but beyond that, we cannot tell you what it's made of. Could either be iron-rich compounds or it could be like a comet with organics. And that's all the data we will ever have, so I can't tell you any more about its composition, except that I don't think it's titanium spacecraft hull. And to tell you the truth, on the first few days when we got the color, I actually looked up what the spectral signature of titanium would be. And to me, unfortunately, it's red.
We're going to start going in that direction. I think what exactly it might be and some of the really exciting theories that are out there. But when we talk about the trajectory of the object and that acceleration that you spoke about earlier, can you talk a bit about what we now know about the trajectory and that acceleration?
Yeah, that really excited a lot of people when they said, okay, it's accelerating. Isn't that a little bit strange? But in fact, it's not strange. We see comets accelerating all the time. And this is because the comet doesn't outgas uniformly. It outgasses where there are cracks in the crust, where there's a little more ice near the surface. And so you get jets of material coming out. And that behaves just like a rocket thruster. And so it pushes the comet. It speeds it up or slows it down. We see this in comets all the time. Now, to model the orbit of Oumuamua, when they took gravity only, it didn't work. And when they added a simple acceleration that was pointed directly away from the sun at a strength that was proportional to the inverse of the distance from the sun squared, it matched perfectly. And so now we know that it's accelerating away from the sun. And that's exactly what we see with many comets. It's the same formalism. So that seemed to fit. On the other hand, there's a lot of other things that are natural that can cause an acceleration. Things such as if you're flowing through a medium with friction, it would slow down. That's the wrong direction for us, so we threw that out. There's an effect called Yarkovsky. When an asteroid's rotating, sunlight can heat up the surface unevenly, and then the heat that's re-radiated again acts like a little rocket thruster. But that's a really subtle effect, and Oumuamua was accelerating too much, so that one had to be thrown out. Sometimes if an object breaks into two, it will give it a little push, but that should be a spontaneous event. Yet every time we broke up the data into small segments in time, we always saw the acceleration. So in the end, we had to throw out everything. There was one more possibility, and that is solar radiation pressure. The sunlight hitting a surface can bounce off the surface, and then it gives it a little push. But the only way that's effective is if you have a large surface area to thickness ratio or density so that it can push it along. And because that's not physical for something in the solar system, we also threw that out. So the only thing left was comet outgassing, even though we saw no gas or dust.
And you're basing that more on the behavior as opposed to actually observing the outgassing.
Yeah, and we had a very sensitive search for dust. And we stacked all of our images together and tried to really hunt for dust near the body itself. And it turns out if you had tiny, tiny dust, typical of what we see in comets, about the size of cigarette smoke or bacteria, we could have detected even a couple of pounds of dust ground up that small. And so that's a tiny amount of dust, and it just wasn't there. Now, none of the measurements for gas, a few people tried to go after gas, but it wasn't sensitive enough, and we weren't observing in the right wavelength. The only telescope that tried to look for gas that had a chance of seeing it was the Spitzer infrared telescope in late November. And they waited, you might ask, well, why did they wait so long? It's getting fainter and fainter and fainter. It dropped by a factor of 10 in brightness in the first week. And by late November, it had dropped by about a factor of 200. So why wait that late? Well, Spitzer is an infrared telescope, and it can't point anywhere near the sun. So it had to wait until it was legal to point it. And at that point, the Spitzer team did not see Oumuamua at all. So all they could put was upper limits. And so they put some upper limits on gases such as carbon monoxide and carbon dioxide, which are typical comet gases. And they said, don't see any of that either. But their limits were high enough that it could still have been there and pushed the object.
So let's talk about the origin or the possible origin of the object. Anything you'd like to say about that?
Well, yeah, let's start with slide 2, which shows a graphic that shows the trajectory through the solar system so people can get a feel. And starting on the left path, you can see it approached from above the plane of the solar system, whipped around past the sun, and then went outbound. And in the inset, you can see that it really did come close to the sun inside the orbit of Mercury. So it would have been quite well heated. And then you can see the little dot on the outbound leg, which shows the point at which we discovered it. It had already passed Earth. So it came from the direction of the constellation Lyra, the bright star Vega. And people were excited because we know that there's some young planetary systems there that are just forming. And so the idea is that what you want to do is try and get such precise positional data that you can trace its path backwards in time. And so we took really detailed measurements. And the problem is, while we have an excellent orbit of Oumuamua, you can't just rely on its orbit because all the galaxies and the stars in the galaxies are moving. And so as we're tracing its path backwards in time, we have to know where the stars were backwards in time. And so it was fortunate in 2018 that the Gaia telescope survey, whose duty was to measure precise positions and velocity of stars, did a huge data release. And so one of our team members actually did the calculation of moving 7 million stars backwards in time to where they would have been to try and trace Oumuamua's path. And what we were trying to do, did you pass close enough to any young star system that you could have been kicked out of that young star system? And the answer was there were 4 systems that it might have been close enough to, but there was a problem. It was going too fast. And the normal process, and in fact, if you could bring up slide number 3, we have a picture of what a young solar system might look like. And in this picture, you see in the right foreground a giant planet, Jupiter, a Jupiter-like giant planet, because this is an artist's impression. If one of these tiny little planetesimals comes too close, it can give it a kick and throw it out. But it doesn't have enough energy to throw it out really fast. The problem with Oumuamua was, while we found 4 candidate systems where it passed close enough, the velocities were way too high. So we knew they weren't right. And so in fact, while we did our best, probably this experiment is pointless because unless this was recently ejected nearby, there's no chance you're ever going to know the star positions well enough to do this experiment.
In a lot of our conversations so far, I keep coming back to thinking it must be somewhat frustrating for you and the others that it was here with us for such a short amount of time, and there's no second chance.
Not with this one, but you get a second chance if we can find more of them.
Yeah, and we'll come to that. So the Harvard astronomer Avi Loeb has really wanted the world to take seriously an alternative hypothesis, let's call it that Oumuamua could be, or could have been, an alien space probe. I know that most astronomers disagree, but maybe you can give us some points, some arguments on both sides of that proposition.
I can only give you some arguments on the side that I disagree that this is an alien spacecraft. I think it's great to actually ask the question. And I really wish what he would have done was engaged the public in a conversation of what would it take to convince us that this is alien technology. And in fact, there were a couple of experiments that were done with Oumuamua to test that. And I know reporters had asked me, isn't that silly? And I said, no, why wouldn't you do the science? And so what they did, there was the Square Kilometre Array in Australia that in November looked at Oumuamua at radio wavelengths. And then again, the Breakthrough Initiative used the Very Large Radio Telescope in early December, I believe, to also listen for signals. Neither of them detected anything. And the Green Bank telescope was extremely sensitive, and they could have picked up a signal equivalent to, say, our Dawn spacecraft in the asteroid belt. So whatever this was, it wasn't broadcasting radio signals, but you have to do the experiment. Why wouldn't you? That's a cheap and easy experiment to do. And in fact, it was useful for science because that placed some limits on water outgassing in the radio also. However, what he's claiming is because we didn't see gas, that it therefore has to be this solar radiation principle of, the sunlight pushing gently on what he called a solar sail, because this is a technology that we're thinking of for spacecraft propulsion. You don't require any fuel. It's just a thin, very thin sheet. And so he estimated that you'd need something less than 1 millimeter thick. But it's still, we already knew its size from its reflectivity. So the thing that I find fundamentally wrong and he didn't address was, how do you get a light curve that has a ratio of 10 to 1 when you're going from something really large, 100 meters, down to millimeters? That's not 10 to 1. Furthermore, it was tumbling, like a wobbling top. And for solar radiation, anyone who's a sailor knows a tumbling motion is not a good thing to do when you're trying to sail in the wind. So my problem was he did not address all of the science. He picked parts of the science that fit his hypothesis. And I don't think that's a good way to do science. The question is appropriate to ask because that's the way you discover new things.
So I want to talk about what you would have done had you been able to look at that and other hypotheses. And I'm going to come back to your TED Talk. I recall after you came back from the TED Talk, you and I were talking and and we joked about the fact that at one point in your talk, you started speaking about if only we had had the opportunity to send a probe up there, intercept it, and send back actual data. But you said, unfortunately, today we don't have that sort of fast response capability. And just as you were saying that, the camera switched to Jeff Bezos from Amazon and Blue Origin. I just thought it was such a funny quirk of the program that it almost seemed like you were calling him out and saying, come on, we need this technology and we need it yesterday. So if you had had the ability, and if we had had the forewarning, would that have been top of your list to send up an intercept?
Well, absolutely. But before I get into more detail on that, I don't know that it was just coincidence, because I had told the handler at TED I would really like to look at him when I said that part of the talk. And I was nervous, and I went out and I looked, I peeked around, I said, I don't see where he's sitting. And he said, well, he's a bald guy. I said, half of them are bald. So he went out and he said, he's going to be hard to look at because he's sitting way over at the side. So during the talk, at that point, I did turn my head to look to the right, but I couldn't see him. So I'm glad the camera looked that direction. We certainly do have the technology that could have reached Oumuamua. I know some engineers at JPL had actually worked out a trajectory. There were a couple of science papers that were published saying how you could do it. You'd have to be chasing after it, and it would take a long time to get there. And you would be about at 100 astronomical units, where that's Earth-Sun distance, so way out at the outer edge of the solar system, planetary region. And it would be so dark that I think doing any science at the object, and you'd have to navigate at the last minute by seeing it, would be very difficult. So I think the way to go in the future is to have a spacecraft ready to go, something that's either already built and on the ground that you can launch, or something in orbit that's sitting there waiting for something. The in orbit sitting there is not as desirable because it will get damaged due to the radiation environment over time, or if you have fuel on board, run out of fuel. And on the other hand, if you launch from Earth, you have a lot more thrust, so you can get to many more places. But the Europeans are actually experimenting with this with a Comet Interceptor mission, which will be sitting out in space for a few years waiting. They're waiting for a long period comet. They're hoping for an interstellar object, but I think the chances that they're going to get one at the right time is very small. So I think we need a new style of missions from NASA, one that's all ready and you just launch it immediately. And also because no matter what, we're not going to have a rendezvous where you can sit and stay at the object. It's too much energy. So it's going to be a fast flyby. And so I think the best way to do this is with a miniature fleet of spacecraft, CubeSat style, that are attached to a mothership. And of course, UH is developing these small sats. So I think we have the opportunity for getting in on some of this nice technology. And what you can do with that, NASA is very conservative. You don't want to have a hugely expensive spacecraft get too close to an object, and that limits what you can do. But you could launch the CubeSats from the mothership to get close and assume the risk, and then transmit the data to the mothership. So I think that's going to be the new style of mission if we want to study one of these.
Yeah, and thank you for mentioning the small sat program here. For many of our viewers, they might not know about the Hawaii Spaceflight Lab, and also the fact that HIGP in SOEST presently has two different instruments working on Mars. So certainly the university has many different areas covered in regards to encountering and deciphering what objects, near Earth objects, might be. So let's go to the next obvious jump, and that is unidentified flying objects, UFOs. They're all over the news. There was the release of the government report on several unusual encounters. We'll just leave it at that. There was, I think, a report being released today to Congress. Also, there's an upcoming documentary. I think you will be part of that documentary. So taken all together, what's your view on what we see, at least from the declassified information that has come out so far?
Well, I know everyone was very hopeful that this would say there's aliens out there, but in fact, the declassified document more or less says there's no conclusive proof that any of this is alien technology. Moreover, it's not US technology, but we don't really know what this stuff is. And part of the problem is you have to have a lot of data to really understand what something is. We saw that with Oumuamua. the Mars meteorite that came back, hundreds and hundreds of papers, and people still aren't entirely sure everything that's in there. So you have to treat it much like a murder investigation and really spend a lot of resources on each of these to figure out what it is. And we usually don't have enough data. So I think these UFO reports are interesting, and I can't say one way or another without doing an investigation, which is what you do for science. But I certainly think the possibility that there's life out there is real. Maybe not visiting us on Earth in technological vehicles, but I think it's almost certain that there must be life elsewhere.
That is something we've heard many, many times. I remember people like you and I grew up with Carl Sagan, and maybe you'll tell me that that was one of the reasons you decided to study astronomy at MIT, but certainly it was one of the pulls for science for a generation of young people. So tell us what an astrobiologist does. That is, you are regarded as an astronomer, but also an astrobiologist. So what is that, and how does one become an astrobiologist?
It's kind of funny that the standing joke is it's a field of science without any content because we haven't yet discovered life anywhere else. But it's a bigger field than just looking at life elsewhere. It's understanding the origin of life, understanding where you could have life in the solar system and elsewhere. What is a habitable environment? What are the ingredients you need for life? And how does a habitable world form? And so then of course it's the search for life elsewhere, including technological signals. But my role in this is I'm really keen to understand how you form a habitable world, namely, how do you get the ingredients for life onto a planet that's at just the right distance from the stars, such as the Earth. And so right now I've been focusing on understanding how Earth got its water.
So you're hinting at suggesting that Earth is not necessarily utterly unique in hosting life. It's your belief that there likely is life elsewhere.
Oh, absolutely. As I looked it up because I wanted to see how many exoplanets today, and as of today, we've got more than 4,400 known exoplanets, with about 7,400 more candidates that are likely to pan out as exoplanets. And among those, there's over 3,000 planetary systems. And within those, many of those planets are actually in the habitable zone, which is the special distance from the sun where liquid water could exist on the surface of a world if it had an atmosphere. And we have seen throughout history, on the history of Earth, that life started very early, almost as early as the Earth was cool enough to have oceans. And it will probably persist far into the future, but of that whole period of time, it's mostly microbial throughout that whole history. So I think it'll be a very narrow slice of time that has even macroscopic life, plants and animals, and an even smaller slice with technology. So I think there's absolutely life out there, but I think the most likely life that we might detect first will be microbial life, and hopefully within our solar system.
Wow. Fascinating. I'm going to switch gears a little bit because one of the things that we all, I know our colleagues here at Mānoa were impressed with was the speed at which virtually every observatory on Earth engaged as partners in this rush to discovery about what this new object was, where it had come from, where it was going. And maybe you can describe exactly how that came about and give the viewers a sense of the numbers of people and observatories that joined in this partnership to study this object.
Well, part of the reason that I got involved was because Richard Wainscoat knew that I had many roles in leading huge teams of people for space missions to support the ground observations. So I had a lot of connections with telescopes. And normally you would get time on a telescope through a really slow process. You write a proposal, It's reviewed months later. You find out if you got a night or two. So it's really precious resource. You don't have time for this with something like this, but you still have to write a proposal. It's basically a very short proposal that goes to a director of an observatory. And these are really sharp people. They realize this is an exciting discovery, and all of them said yes immediately, giving us time. But then you've got to prepare the observations. And so you rely on your network of colleagues to do this. And everybody said yes, including coming up to perfect strangers and asking them, could we use some of their time, their hard-earned time, to get data? And everyone was excited to do so. That'll probably happen for the first few. After the first few, yeah, we've got so many of these, we don't care anymore. But it was a frenzy, because then you're managing the data that's coming in at night. You have to analyze it immediately and start writing a paper. So I was like mission control in my office. I was perhaps napping in the office, although I'm sure there's rules against that. But you had to stay here 24 hours a day to keep on top of everything to get it all done in a week.
Wow. Yeah, it was an exciting time. So I know we likely have some young people watching, perhaps I should say young and old, who have the same question. What brought you to this career? I mean, you've been fabulously successful, but I know that it's quite a competitive career. And I know in your case, very, very satisfying. Maybe you can tell us a little bit about your journey in your career, and perhaps even some suggestions, some advice for someone out there who might be considering a career in astronomy.
Well, I know you're going to grin at this. It was aliens that brought me to this career. Actually, 1967, Star Trek came out, and I was just fascinated with that show. I was 8 years old, and we watched it every week in front of the TV, and I was so excited. I said, that is what I'm going to do. And so I used to camp outdoors at night in the summer in our backyard and look at the stars. And my parents were shaking their head and kept saying, you better wait and see if you like physics. I was stubborn. I said, I am going to like physics. I had no idea what physics was. And it turned out I did not like physics. They really ought to start physics with optics, not with frictionless slabs sliding down inclined planes. That's not very interesting. But I stuck to it. And, you need something that stimulates your imagination. And I always felt that there must be something else out there. I wanted to be an astronaut for a while, but then I decided the research path was the way to go. So it was indeed aliens that brought me to this career.
There is some irony in all of this. Yeah, that's great. Thank you. So when this first came about, when the object came to attention, obviously it was from our observatory on Maui, which is obviously the part of the Near Earth Object Observations Program. Maybe you can talk a little bit about that program and its importance from a lot of different aspects.
Yeah, NASA is funding this program because it's for planetary protection. And most people don't realize how frequently bodies come very close to the Earth. So they want to discover everything that's potentially hazardous. And I believe the current mandate from Congress is that we need to discover more than 90% of all these near-Earth objects that have diameters greater than 140 meters. And Pan-STARRS is really the leader in discovering these things. In addition, it's also leading at discovering not hazardous things, but things like Oumuamua or very faint fuzzy comets in the outermost solar system. So it's really providing a rich array of science for planetary folks. But in addition, the Atlas survey, also in Hawaii, there's 2 telescopes here, one being built in South Africa and one in Chile, is looking for the really big things. So we've got a really robust program in Hawaii to search for these potentially hazardous objects.
And does the program have potential for identifying and recognizing objects like Oumuamua that would be, I guess, providing information in sufficient or with sufficient lead time that we could send a probe? Do you see us having that capability, perhaps in conjunction with other partners from other parts of the world?
Absolutely. There's been a second interstellar object that's discovered in August of 2019. And that was actually discovered by an amateur because he was doing something the big telescopes can't. He was looking really close to the horizon in twilight. And this one was quite bright. And we were lucky. That one was on its way approaching the sun's. So in fact, we had all the way until this past February and March were our last observations of that one. But that looked more like a regular comet. Once we get the Large Synoptic Survey Telescope, the Rubin telescope online in Chile, that is a much bigger survey telescope, and it will start finding more of these objects further from the sun. But just from this one Pan-STARRS discovery, we are estimating, and this is kind of a scary but interesting fact, that we're estimating that there might be one of these objects at any one time in the solar system between us and the sun, which is a region that's very hard to survey.
Wow. And from the perspective of, I have to ask this question, of a threat to the planet, what's your view? I mean, I know this in some ways is unfair and we continue to gather data, but I remember you were saying even before we started the program, there are many objects out there. They vary both in their size and their trajectory, but some might at any given time pose a threat to the planet, correct?
And in fact, most people don't realize how close Oumuamua came. It came within 63 Moon-Earth distances. That's really close, and we didn't see it till after it had passed by. And at the time, it was moving about 60 kilometers a second or 133,000 miles per hour. And given its estimated mass, the energy release, if it had hit, would have been about 100 million times that of the bomb that was dropped in Japan in World War II. So that's a big impactor, but that is not one that would be dangerous to Earth, certainly to city levels. The threshold that they're talking about, regional damage, is 140 meters in diameter. So it's close to Oumuamua size. And then a 300-meter one is almost certain to hit in the next 500,000 years. So, something will eventually hit us, but the hope is that we get the ones that we can do something about before they hit us. And that's the point of funding surveys like Pan-STARRS.
Yeah, it's good to let's put it in perspective. I think many viewers would know of the impact in the early 1900s in Siberia. Working backwards, what is the feeling about the size of that object, and how would that compare to Oumuamua?
It was much smaller than Oumuamua, and it was probably very fragile because it probably burst in the atmosphere. And it knocked down trees in Siberia over a 2,000 square kilometer region. And there were a few eyewitnesses accounts of reindeers being tossed into the air. And I know it was recorded as far west as London. So that would have been devastating had there been a city there, but fortunately it was uninhabited mostly. So we do want to watch for these things. And the real danger is things coming at us from the direction of the sun where we can't survey from the ground. So there are proposals to have spacecraft that are in space that can point in that direction.
So we're coming to the end of our time together, unfortunately, and I can't believe the time went so quickly. I want to give you an opportunity to maybe speak about something that we haven't covered that you'd like the audience to know.
I really think we need to put a little bit more money into these space missions. This will give us so much more opportunity to study not just Oumuamuas, but some of these new small bodies that are being discovered. Had we had a spacecraft that could have taken a single close-up picture of Oumuamua, it would have really resolved many of these controversies. So I think the big message is science is exciting, space is exciting, and this is the area for exciting careers for the young. Get into technology, get into space technology, and Hawaii is really the place to be for all sorts of space, astronomy, and technological jobs. So I think it's an exciting era to be young.
Yeah, I agree with you so much. I know we were talking before we came on about the astronomy program here at Mānoa, and you said it's growing rapidly, isn't it?
Yeah, both the undergraduate program, and we have a very healthy graduate program that's increasing in size too.
Yeah, what an exciting area, and a vibrant area for science in so many ways. We've been discussing, just in the discussions here, we've been discussing everything from optics to materials science, and obviously we're talking about spacecraft, satellite, and other technologies that require engineering as well as sciences. I'm sure computer science comes in a big way in the analysis of the images that you've been discussing.
Absolutely. And I keep talking to Jason Lee in the Cyber Canoe Lab, because I think for some of these space missions, to be able to visualize the target that you've approached up close and manipulate it in 3D is the way to go for science. So I'm hoping we can get more collaboration between computer science and the spaceflight lab, astronomy, because I think there's new and innovative ways we can do science.
And finally, I want to talk about international cooperation. It seems so essential for success. You mentioned the telescope in Chile. You mentioned the fact that observatories all around the world basically stop their normal way of doing business in order to focus in on Oumuamua and work together. I remember the paper in Nature that first came out. I think the first author was a student of yours, correct?
No, the first author, that first paper, I was the lead author.
Okay.
We sort of rotated the authors on each of the papers, but we did have student involvement on several of them. So it's been exciting. Yeah.
Yeah, I remember the student participation, but I also remember the length of the list of authors, which was really extraordinary, and authors from everywhere around the world. It just seems that, and I guess the direction I'm going is we are at a time where there is some distrust, some caution, some of it warranted, maybe some of it not so warranted, about the levels of international cooperation. But in your area, in this area, it seems absolute that we cannot do it without being a partner and close collaborator with other nations. Is that your judgment as well?
Absolutely. And that was especially important for the Deep Impact mission, because we had the entire world watching the event. And there was one notable student on one of the papers. He even gave up his wedding night. He could watch the event. And I asked them to send me pictures of themselves. And I said, wow, you're really dressed up for observing. He goes, because I just got married. And he was a graduate student in China.
Wow. That almost seems like the perfect way to end our time together. Dr. Karen Meech, astronomer and astrobiologist extraordinaire. I'm going to give you that title today. It has been so good talking with you, and I want to thank all of our viewers. We have hundreds of them on the line today with us. And before we sign off, I want to give my sincere thanks, heartfelt thanks on behalf of Karen and myself and and the entire team, to all of the sponsors of today's event. The UH Foundation and its Office of Alumni Relations have been amazing in supporting this event and the entire series. The Better Tomorrow Speakers Series and our partners, Kamehameha Schools and the Hawaii Community Foundation. To those partners, thank you so much. And I know we get so much out of these webinar series. Karen, I think you've inspired a number of people, I hope a lot of young people today, to follow in your footsteps and pursue a career in science. So thank you so much, Karen.
Thank you for having me. It's been great.
Aloha, everybody.